Okay, so it's been a while since I recorded some videos for my Unit 3-4 Methods class, and that's because we've had quite a break in preparing for the Application SAC, and we're now ready to resume with some new content, finishing off the calculus component of the course by looking at integration. So integration is the reverse process of differentiation, and so it's sometimes also called antidifferentiation. I'm aware that that's not a commonly used word around the world, so if you are tuning in from somewhere other than Australia, and or maybe even other than Victoria in Australia, and you aren't aware of the word antidifferentiation or antiderivative, then it may well not be a word that exists in the maths community in your neighbourhood. So I would use that word slightly loosely, but here in Victoria, we happily call the reverse process of differentiation antidifferentiation, and we can also call that integration. Okay, so we want to today look at, in these early couple of videos, the first 3 videos here, we're really just going to look at rules and techniques for differentiating various functions, and then we'll go on to look at the process of calculating definite integrals and how that connects to area. And a bit later on, we'll come back and add in circular functions and then some sort of applications and other problems later on. So let's begin with the most basic sort of power function or polynomial function, so x to the power of n, and we're also going to look at a times x, ax plus b, all to the power of n. So what we want to think about throughout this entire topic as we're establishing all our rules is how we use what we know about derivative to then make inferences for antidifferentiation or for integration. But before that, let's just check on some notation. So this is our notation for antiderivative. So on the left-hand side here, we have the antiderivative or the integral of f of x with respect to x. So in the same way when we differentiate y, we need to know what variable we're differentiating with respect to, dy dx with respect to x. We also need to know when we're antidifferentiating what is the variable that we're differentiating with respect to. It is very, 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 very common for students to omit the dx, and if you do that, your answer is wrong, your working is wrong, and you will lose marks. So please, let's make sure that we understand that the dx and the integral sign, they go together. They should never be seen without one another. The minute you write integral, you then should have d. Now, it might not always be x, but if your function's in terms of x, it would be dx. If your function's in terms of t, you'd be differentiating with respect to t. If your function's in terms of theta, you'd be differentiating with respect to theta, okay? But always an integral sign and d something, okay? And I don't want to harp on too much about this capital F of x notation because it's not actually that common. But the antiderivative of f of x with respect to x is sometimes referred to as capital F of x. Okay, that would really need to be defined in the question, but just in terms of ease here, and the textbook uses it occasionally, I'm going to refer to it. But I want you to be a bit cautious about that. I wouldn't just write capital F of x if I meant the antiderivative, unless it had been defined by the question. So generally, what we have here is we have our function. We know that if we differentiate it, we get f dash x. If we antidifferentiate it, we get capital F of x. Okay, again, let's be a bit loose with how we use that. Or let's be a bit careful about how we use that, I should say. So essentially, heading in this direction requires antidifferentiating. So if you know about the derivative and you want to get back to the original function, you're going to be antidifferentiating. Similarly, if you know about the antiderivative and you want to get back to the original function, you're going to need to differentiate. So heading to the right, differentiating, heading to the left, antidifferentiating. Okay, let's start with some really basic derivatives and take some inferences from there. So consider the polynomial functions below and calculate their derivatives. Okay, so we know x squared, so we know when we're differentiating x to the power of n, that it's nx to the n minus 1. Okay, so derivative of x squared is going to be 2x to the power of 1, so it'll just be 2x. The derivative of x squared plus 1, so derivative of x squared is 2x, and the derivative of a constant value is 0, and so we just get 2x. And so the derivative of x squared plus 24, well, that's also 2x. And the derivative of x squared minus 5, well, that's also 2x. And differentiating x squared minus 56 also gives us 2x. Okay, so this actually presents us with a problem, because if I say to you, okay, well, given what you've learnt here, what's the antiderivative of 2x? Well, it's clearly going to have an x squared in it, but how do I know whether it's plus 1 or plus 24 or minus 5 or minus 56 or plus 738? Okay, and that's where when we anti-differentiate, we must include a general constant value. Okay, so what we learn here is that the antiderivative of 2x with respect to x is certainly going to be equal to x squared, plus there could be some constant value. And we would need to know further information about the problem in order to be able to calculate what that constant value is. So if we're calculating a general antiderivative, and that is when saying that I mean when there's no limits here, and we'll talk more about that down the track, there should always be a plus c value. Okay, we've now hit upon two key places where you'll lose marks through carelessness: leaving dx's off your integrals and leaving plus c's off when you have general antiderivatives. Okay, so making sure that those two things are done well. Okay, let's think therefore about anti-differentiating x to the power of n, and we're going to do this through thinking about what we know about differentiating x to the n. So we know that when we differentiate x to the power of n, we get n times x to the power of n minus 1. Okay, so we multiply, the process we use is to multiply by the power, and then after we've done that, so we don't change the n, we first multiply by that power, so bring the n down, then we subtract 1 from the power. Okay, so we know that. And so then if we think through anti-differentiating, we know that we do the reverse thing. And when we reverse a process, we not only do the opposite things, but we have to do them in the opposite order. So the first thing we're going to do is the opposite of subtracting 1 from the power, which is to instead add 1 to the power, or exponent. And then after we've done that, we're going to do the opposite of multiplying by the power, which is to divide by the power. Now, because we've done this as the second step, we're dividing by the new power. So after having added to the power, we're then dividing by that new power. Okay, so if we follow those steps here, the antiderivative of x to the power of n with respect to x, we're going to add 1 to our power, so it's going to become x to the power of n plus 1, and then we're going to divide by that new power, which is n plus 1. Okay, you might also see that written as, you might prefer to write that as 1 over n plus 1 times x to the n plus 1, and it depends on what you're dealing with as to which way you prefer to think about it. Obviously there's a restriction here. This rule only applies where n doesn't equal -1, because if n were to equal -1, we'd have big alarm bells happening here. We'd get a denominator of 0. And so we'll talk separately about when n equals -1. So this rule doesn't apply for if you were doing integral of x to the power of -1 or integral of 1 on x. We'll talk separately about that in the next video. Okay, but every other power, positive, negative, fraction, whole number, whatever it might be, this rule is going to apply. Okay, some other properties we need to understand when anti-differentiating is if we have the antiderivative of a sum or difference of two functions, so antiderivative of f of x plus g of x is just the same as finding the antiderivative of f of x and adding that together with the antiderivative of g of x, same if it was subtraction. The other thing we note is if we have a constant value times a function, that constant value is not going to change how you anti-differentiate. So you can just take the constant out of the integral, you're just integrating f of x and multiplying that by the constant value. Okay, so that means in a problem such as this, and I wouldn't write out all these steps every time. We do a lot of this in our head, but I want to be clear about what's happening here. So the first thing is we're subtracting two things. So actually this is two separate integrals. It's the integral of 2x squared with respect to x minus the integral of 4x with respect to x, which is essentially using this property. And then we've got some constants here. So that 2 is not going to change how we differentiate antidifferentiate x squared. So the 2 can come outside the integral. So it's just 2 times the antiderivative of x squared minus, and again the 4, the constant value, can come out of there, 4 times the antiderivative of x. I'm going to write that as x to the 1 so I can do that antiderivative. So the antiderivative of x squared, we add 1 to the power and we divide by the new power, so it's x cubed on 3, minus 4 times the antiderivative of x to the power of 1, we add 1 to the power, so it becomes x squared, and we divide by that new power on 2. And then let's just tidy up those fractions where we can. So that is 2x cubed on 3 and minus 2x squared. The 4 and the 2 will cancel down there. And, sorry, left off my all-important, plus c. Okay? There may well have been a constant value that when we differentiate would have disappeared, and so therefore when we anti-differentiate we can't know whether or not there was a constant without further information. Okay, let's work on some further antiderivatives. So antiderivative of x cubed plus 4. Now I'm not going to write out the steps of it being a separate integral, but I do want you to think about anti-differentiating a constant value. So I'm just going to write this. Let's think about that as perhaps being 4x to the 0, because x to the 0 is 1. So 4x to the 0, and that might help you to think through how this still fits the same antiderivative rule. I wouldn't say you need to write that out, and you certainly wouldn't need to do it every time once you've got the hang of what's happening. Okay, so antiderivative of x cubed, we add 1 to our power, x to the 4, divide by our new power, which is 4, plus 4 times x to the power of, we add 1 to the power, so it's going to become 1, and we divide by the new power, and plus c. And so we're going to have x to the 4 on 4, or you might choose to write that as 1/4 x to the 4, and then we're just going to have plus 4x plus c. So when we anti-differentiate a constant value, so anti-differentiating k, we get kx. And that makes sense, because we know that when we differentiate kx, we get k. Obviously plus c as well. Okay, part B. So antiderivative of 3x squared, so I'm going to have 3x, I'm going to add 1 to the power, which becomes 3, divide by that new power, plus 4x, we're adding 1 to that power, which -2 plus 1 is -1, divide by that new power, and then 3 will become 3x, and then we've also got plus c, and let's just tidy up our fractions, so that's just x cubed, this is now minus 4x to the minus 1, plus 3x plus c. You can write 4x to the minus 1 as 4 on x if you'd prefer. Perfectly fine either way. Okay, part C. So the other thing I want to be really clear about is that there is no product or quotient rule or chain rule, although there's ways we can think through simple chain rule problems, but there is no product or quotient rule for anti-differentiating. So we must work on simplifying our expression before we anti-differentiate. And this is a game where notation is really important. Often students make errors in notation here. So until you've actually calculated the antiderivative, you still have your antiderivative with respect to x. Let's just focus on simplifying what's happening in there, okay? So I'm going to break that up into two separate fractions. It's 2x to the 8 over x cubed minus 5x over x cubed. Again, I probably wouldn't write out this line, I would do that algebra in my head. 2x to the 8 over x cubed, subtracting those powers gives me 2x to the 5, minus, that's 5x to the 1 over x cubed, so that's going to be 5x to the power of -2, subtracting those powers. We are still anti-differentiating with respect to x. We haven't actually done any anti-differentiating yet, all we've done is simplify the expression within the integral. Now when we take the antiderivative, we'll lose our integral notation. Okay, so antiderivative of 2x to the 5, we add 1 to the power, divide by the new power. Antiderivative of 5x to the minus 2, we add 1 to the power, divide by the new power, plus our constant value. Simplifying our fractions, so 2 on 6 is 1 on 3, so x to the 6 on 3, or you can write that as 1/3 times x to the 6, and then minus minus here, so it's going to be plus 5x to the minus 1. Again, you can write that as 5 on x if you prefer, and plus c. Okay, part D. So here we have a product of two functions, okay? A sort of complicated square root / cubic function multiplied by a linear function. You cannot anti-differentiate it in its current form. So what we learn here is that the antiderivative of f of x times g of x does not equal the antiderivative of f of x times the antiderivative of g of x, okay? So again, there is no product rule, and that's certainly not it. You must simplify so that you only have addition or subtraction within your integral before you then go about anti-differentiating. Okay, let's expand out our brackets. So I am not anti-differentiating yet. I'm going to first of all write root x square root of x is x to the half plus 2x cubed times x plus 5 dx. Then let's expand out those brackets. So x to the half times x, adding those powers is x to the power of 3 on 2. X to the half times 5 is 5x to the power of a half. Plus 2x cubed times x is 2x to the 4. Plus 2x cubed times 5 is 10x cubed. Again, we haven't anti-differentiated yet, so it's still the integral of all of that with respect to x. Now, however, we're in a position to be able to anti-differentiate, so we lose our integral sign now that we're actually calculating the integral. So, fractions, we're adding 1 to the power, 3 on 2 plus 1. 1 is 2 on 2, so 3 on 2 plus 2 on 2 is 5 on 2. And then we're going to be dividing by that new power. Plus 5x, add 1 to a half, that's 3 on 2. Dividing by that new power. Plus, add 1 to the power, divide by that new power, plus, add 1 to the power, divide by that new power, and then we have plus c. Let's focus on simplifying. So we know that if we are dividing by 5 on 2, we are multiplying by 2/5. So this is 2/5 of x to the 5 on 2. And again, you can write that fraction separately, 2/5 times x to the 5 on 2 if you prefer. Dividing by 3 on 2 is timesing by 2/3. So timesing 5 by 2/3 is going to be 10/3. Okay, so again, you can write it as 10/3 x to the 3 on 2 if you prefer, or you can write it as 10x to the 3 on 2 over 3. 2/5 doesn't simplify any further, we'll leave that as it is. 10 on 4 will simplify, that's 5 on 2. As I said, nothing wrong with writing this as 2/5 times x to the 5 on 2 plus 10 on 3 times x to the 3 on 2 plus 2 on 5 times x to the 5 plus 5 on 2 times x to the 4 plus c. They're exactly the same thing, okay? Alright, next we want to look at generalizing that a bit further. So anti-differentiating ax plus b to the power of n. So we want to again start by thinking about how do we go about differentiating ax plus b to the power of n. And we know that differentiating something like this requires the chain rule. Okay, so we cover up our inside function, ax plus b, and we differentiate the outside. So we've got something to the power of n. So when we differentiate, it's going to be n times that something to the power of n minus 1. And then we have to multiply by the derivative of the inside, which in this case, it's a linear function. Derivative of ax plus b is just a. So to differentiate ax plus b to the power of n, we multiply by the power. So we multiply by n. We then subtract 1 from the power. So the power became n minus 1. And then we multiply by a, which is part of the chain rule. Okay, we multiply by the derivative of the inside, which in this case is just a constant value a. Now if the derivative of the inside, let's say, don't write this down, let's say this was ax squared and the derivative of the inside was therefore 2ax. We can't reverse that process because this involves x as well. So the opposite of multiplying by 2ax in terms of when you're integrating with respect to x is not just dividing by 2ax. So the only reason we can reverse the chain rule in this instance is because the inside function is a linear function, and therefore the derivative of that inside function is a constant value, and the opposite of multiplying by a constant value is just to divide by that constant value. Okay, so we can reverse it only because we just have a linear function inside the power of n. If it was anything else, we would need other techniques to be able to anti-differentiate. Okay, so to anti-differentiate, we're going to reverse this process. And remember, it's not just doing the opposite steps, but it's also doing them in the reverse order. So the first thing to think through is that we're going to divide by a. Then we're going to be adding 1 to the power. And then we're going to be dividing by the new power. So we just divide by the power, but because we've added 1 to the power before that step, we're dividing by what is now a new power, n plus 1. Okay, so differentiating this, we're going to be dividing by a. We're going to be adding 1 to our, let me start again. We've got ax plus b all to the n. We're dividing by a. We're adding 1 to the power, and then we're dividing by that new power. Okay, so once again, this is only going to work if n doesn't equal -1, because if n were to equal -1, the denominator would be 0. So again, we'll look at separately in the next video, how do we differentiate if it's ax plus b to the -1. So again, you can also write that, you don't need to write it all in one fraction, you can write it as 1 over a to the power of n plus, a times n plus 1, which is dividing by a and dividing by n plus 1, and then ax plus b to the n plus 1. With a lot going on, I probably tend to write these in this way, whereas the others, a single term, I tend to be a bit more flexible about that. But either way, okay? Okay, so that little note there is just what I was saying earlier, that in most cases we cannot use a rule to anti-differentiate something that would have been differentiated using the chain rule. It only works in this case because the inner function is a linear function and its derivative is constant. Okay, so that's really important. If it was anything other than a linear function inside the power, you'd need other techniques. Okay, I'm just going to keep this rule in sight so we can see what's happening here. So antiderivative of 3x plus 5 to the power of 6. So this fits in this category. So we're going to have 1 over, as I said, I tend to prefer to use the write the fraction separately here. There's a lot going on. It gets a bit crowded all in the one fraction. So we need to divide by, so we're going to have our ax plus b, which in this case is not ax plus b, it's 3x plus 5. We're going to add 1 to that power, which makes it 7. We have to then divide by that power, but we also have to divide by a, which is the reversing of the chain rule. So a in this case is 3. So 1 over 3 times 7, which is a times n plus 1, and then 3x plus 5 to the power of 7. So that is 1 on 21 times 3x plus 5 to the power of 7. And I forgot to add my plus c. It's okay if you just stick it on the last line of working, that's fine. In fact, let's add it into our general rules here. So plus c, if you're going to write it this way, it should still have a plus c. And let me add it into my general rule back up here where we did x to the n as well. Plus c. Okay, let's have a look at some other examples. So integral of square root of 7 minus x. So again, thinking about how this is of the same format as this. So we know square root is a power of a half. And it might help you to think about it as being negative x plus 7, if that helps you to see it in the same order as the ax plus b. So we've got all that to the power of half. Okay, so the antiderivative of that, we're going to have 1 over, so it's going to be a, which in this case is negative 1, multiplied by the power plus 1, so half plus 1 is 3 on 2. And it's 7 minus x to the power of 3 on 2. So we've got 1 over negative 3 on 2. Again, we're dividing by negative 3 on 2, which is multiplying by negative 2 on 3. Okay, so it's going to become negative 2/3 out the front there, times 7 minus x to the power of 3 on 2, plus c. Okay, part C. 4x minus 1 to the power of negative 3. Okay, so we're in this same format, ax plus b to the power of n. And so we're going to have here 1 over, so the a value here is 4. N plus 1 will be negative 3 plus 1 is negative 2. And we have 4x minus 1 to the power of negative 2. So we've got negative 1/8 times 4x minus 1 to the negative 2. Now, because you've got a fraction and also a negative power, it's probably neater to write this as negative 1 over 8 times 4x minus 1 squared. But it's perfectly fine in the previous line, it's correct. And plus c. See how easy it is to forget? Okay, last thing before we leave it for today is, given extra information, it can be possible to find a unique antiderivative, so to actually calculate that C value. So in example 3, we want to find dy dx in terms of x if we want to find y in terms of x if dy dx is equal to x to the power of 3/4 plus x to the power of negative 3/4, and if y equals 5 when x equals 1. Okay, so if we want to find y, so we have the derivative and we want to get back to the original function. So it's important that we understand that y is the antiderivative of the derivative. Okay, so antidifferentiating the derivative will give us y. So antiderivative of x to the power of 3/4 plus x to the power of negative 3/4. Okay, so let's antidifferentiate that. So adding 1 to 3/4 is 3/4 plus 1 is 3/4 plus 4/4, so 7/4. And then we have to divide by 7/4 plus adding 1 to negative 3/4, so negative 3/4 plus 4/4 is positive 1/4, dividing by 1/4, and then we've got plus c. So again, dividing by 7/4 is the same as multiplying by 4/7. So we've got 4/7 times x to the 7 on 4 plus dividing by a quarter is the same as multiplying by 4, x to the power of 1/4 plus c. Okay, so we've got y in terms of x and c, but we've also now got a point. We know when x equals 1, y equals 5. Okay, so we want to substitute that in. When x equals 1, y is 5, so we know that 5 is equal to 4/7 times 1 to the power of 7 on 4, which is just 1, plus 4 times 1 to the power of 1 on 4, which is also just 1, plus c. So we have 5 equals 4/7 plus 4 plus c. We just want to solve for c here. So let's take away 4, which gives us 1 equals 4/7 plus c, and let's take away 4/7. 1 minus 4/7 is 3/7. So c is 3/7. And so therefore, y in terms of x is y equals 4/7 x to the power of 7 on 4 plus 4x to the power of 1/4 plus 3/7. So if you've got a point on the original function, you can then go on to find c, and you no longer have we call it an indefinite integral, and we've got that c value where we don't know what that actually is. We can actually calculate the more precise integral. And finally, just to have a look at how we anti-differentiate using our CAS. And so there's a number of different ways to access the integral or antiderivative template with your CAS. One is to go through the menus. So that would be menu 4 for calculus, 3 for integral. When we do that, it brings up this integral template with the boxes for your limits. But you'll notice that they're grayed out. So if you just leave them blank, and just enter, let's say, something as simple as x squared, we want to differentiate that with respect to x, it will just then ignore them. Alternatively, well, let's have a look at another way we can get the integral template, and then I'll talk about how else you can deal with that template. So the other option, the shortcut key, rather than going through the menus, is to press Shift plus. You might remember that Shift minus is to differentiate, Shift plus is to anti-differentiate. So if you want to, when you've just opened up this template and you've got the limit boxes, if you don't need those, which we don't yet, when your cursor is in one of those boxes, if you just press delete, it'll get rid of the limits, and then you can just enter your expression in. But really, you don't need to bother getting rid of them, you just ignore them. So let's say we did t cubed, we wouldn't want to be differentiating with respect to x, it would be with respect to t, and so then we get our antiderivative. You'll notice also that your CAS doesn't give plus c, so it's really important that you remember that you need to add the plus c on if you're writing your answer on the paper. The last way you can get the template is through the template palette, and so this is the option down here without the limits, or back on the previous row there's the integral with the limits. Okay, so same template. Shift plus is the quickest way to find your integral, however. The other thing I want to say just before we finish up is that of all the things we cover through this topic, when we get to the end of this topic and you're revising for the SAC, or when we're getting to the end of the year and you're revising for the exam, the one thing of all the things that I teach you throughout the year that none of you ever remember is how to anti-differentiate these. So let's try and make a really conscious effort this year to remember and to recognize and know that we know how to do those and that we can anti-differentiate those. There are versions of these antiderivative formulas on your methods formula sheet as well, which is on the inside cover of your blue booklet. So make sure that you're aware of which versions of the antiderivatives you get, and that therefore you perhaps don't need to remember, and that you can refer to at any time, and which ones you're going to need to actually know along the way. Okay, so the work today is a mixture of questions from exercise 11B and 11C in your textbook.